John's doctor has ordered him to undergo an MRI test to detect the problem of his symptoms. He is feeling anxious about the test and wants to understand more about magnetic resonance imaging. Is a scan in which strong magnets and radio frequency pulse are implemented to generate signals from the human body. These signals, however, are sensed by a radio antenna, and which are then processed by a computer to capture images of inside a human body.
MRI stands for magnetic resonance imaging, so it uses magnets and makes pictures. Clearly we're off to a great start. This device takes advantage of the fact that the human body is mostly water, meaning it has a lot of hydrogen atoms. Recall that a hydrogen atom has one proton and one electron. This proton can be imagined as a tiny magnet. In fact, that's what we're going to call you from now on. So, tiny magnet? No, I'm just kidding. As a tiny magnet, it rotates on an axis with a north and south pole. Normally, the protons in the body are all spinning in random directions. Their axes are not aligned in any particular way. However, if the body is placed in a strong magnetic field, the protons' axes will line up together. This alignment creates one big magnetic vector in the direction of the MRI machine. Now here's the cool part. If a radio wave is sent into the magnetic field, it will cause the field vector to deflect. This deflection makes the protons resonate, or flip their axis of spin. If you have a series of electric coils, you can use an alternating current to create small magnetic fields in separate sections of the body. Different parts will resonate depending on the frequency of the radio wave. When the wave emitter is turned off, the magnet vector will return to its original position, meaning the protons will flip back to their original axis of rotation. When flipping back, the protons will emit the same radio waves they absorbed. The machine receives these waves and plots the intensities on a scale to make cross-sectional diagrams. To make proper images, the machine has to emit a series of radio pulses to emphasize specific body parts, because different tissues relax at different rates. The time of relaxation for a tissue is measured by how long it takes the protons to flip back to their original axes. So with all this fancy tech, what is an MRI good for? Other than just being able to take clear pictures of the human body without causing harmful side effects, they are great at finding diseases. Most diseases are marked by an increase in water content, so the machine can be programmed to recognize these irregularities. Blood, for example, is a great way to track things in the body because it's composed of a lot of water. fMRIs, or functional MRIs, are used to visualize activity in the brain by measuring changes in blood flow. This makes it easier to find abnormalities like tumors and ultimately save more people.
John is no longer nervous about the scan.